Okay, so yeah, today I'm talking about type checking Ruby programs with annotations. So the last talk was about also the type checks, so two talks about the type checking. So let me start with introducing myself. So my name is Soutaro Matsumoto, and the GitHub and the Twitter account is Soutaro, so please follow me. And so probably a good option to introduce myself is to introduce the company I'm working for, or maybe the product I'm spending my time for. But I spent several hours yesterday to think about how can I introduce myself for today. And finally, I found that this should be a good self-introduction for today. So I have implemented 4 type checkers for Ruby for 12 years. So maybe I'm the only one person in the world who tried this 4 times. The first type checker I have tried to implement was when I was an undergraduate student. So it was based on the constraint-based type inference, and the type system has some structural subtyping. So it didn't work very well. So the next one is when I was a PhD student. It's 10 years ago. So it's based on the ML type inference algorithm. And the object typing is based on the extension of polymorphic record types. So this also doesn't work very well. The third one is after that. So I tried to do the control flow analysis. So I implemented analysis called safety analysis. It is almost equivalent to type checking. So it tries to handle some method redefinitions in Ruby programs, but I don't think it worked really well. So, and today I'm talking about the latest my Ruby static type checker. So it is based on the local type inference. So the first 3 type checkers are type inference based. So I assume there is no type annotations in Ruby program, but the latest one is based on the local type inference and structural subtyping. So I want to start with this question: why do we want a type checker? So what we can do if we have types in Ruby? So there are a lot of benefits and a lot of applications of types. So I want to list some of them. So first, it helps programmers to find bugs. So a type error usually means your program calls some method is invalid, or your program is passing an invalid arguments to some method. So you can fix them before executing your program if the type checker finds that, maybe while you are writing your code. So the next one is that types are a verifiable documentation of APIs. So it tells programmers the structure and the usage of APIs. And not only that, the type checking tells if the documentation is outdated. So this is much better than API documentations embedded in comments. So because you never forget updating the documentation. And when it is integrated, type checking is integrated to IDE like RubyMine or maybe Emacs or Vim. So it helps auto completion. So when you are typing the code, method names will pop up, and you don't have to type the full name of the method. It helps refactoring. So when you are changing the name of some method or changing the signature of the arguments, adding new arguments or adding new keywords, removing that, so the type checking will find the locations, the places you have to fix during the refactoring. So IDEs may provide better refactoring features. And the last one is that type information can be used as a basis of more advanced program analysis. So for example, something like the security checking. So there are some security checking tools for Rails like Brakeman, and they can be improved with type informations. So now we agree that we want some type checking. So the type checking for Ruby is not a very new idea. So it was some people have tried for that at least for 12 years. So I want to introduce two papers published about 10 years ago in this talk. So the first one is static type inference for Ruby. So you may know the name of Diamondback Ruby. So the type checker implementation, and the paper is describing that. The second one is, in fact, my paper. So it is type inference for Ruby programs based on polymorphic record types. So as the title explains, the two papers are trying to type inference of Ruby programs. So because they wanted to type check the existing Ruby programs and the existing Ruby programs without modifying them. So as you know, Ruby is an untyped language, and there is no type annotations included in the source code. So if we want to type check the Ruby programs, we need to infer the types from the source code. So let's see the first paper, static type inference for Ruby. So their implementation is still available at Diamondback Ruby. So in fact, we can download the implementation and try that with our programs. So, but it has not updated for 9 years or so. So yesterday I tried to download it, but I didn't build that. So their type system is based on structural subtyping. So the good thing of the structural subtyping is that it is flexible and intuitive and powerful enough to give powerful enough to represent the types of Ruby programs. So, and the bad thing is because of its subtyping type system, so the type inference cannot infer the polymorphic types in the Ruby program. And I want to explain my papers. So in fact, I had a presentation about this at RubyKaigi 2008, 9 years ago. So the type system is based on ML type inference and polymorphic record types. The polymorphic record is a simulation of structural subtyping. So because it's a bit weaker than the structural subtyping, so it's possible to infer the polymorphic types using the polymorphic record types. So the implementation infers the polymorphic types from the Ruby program. So, so this means, this looks that it is a great advantage compared with the Diamondback Ruby. It doesn't infer polymorphic types, but there is serious limitations also. So the limitation is it cannot give types for some of the built-in methods and classes of Ruby. So because it doesn't give types for string or integer, so it means that implementation cannot type check any Ruby program. So the limitation is because of the ML type inference algorithm. It doesn't allow the set of classes called polymorphic recursion. And in the case of Ruby standard library, array and integer and string are polymorphic recursion. So array will be monomorphic. So we cannot put array to string or integer in that case. So it means if we have the two different array objects and we put the integer and to another array string, so then the integer and string types are unified. So this is a really big issue. And it doesn't type the non-regular types. So this is the map method of array. So yeah, this is a quick overview of the two papers and the comparison. So they have some different properties. So the type system is the structural subtyping ones or polymorphic record of types ones. The type inference is different ones, the constraint-based type inference or ML type inference. But maybe the most important one is the limitations. So they both have a really big limitation, and they cannot be practical too. So in short, they are not something very useful. So this is the conclusion about the type inference for Ruby programs. So it's really a sad thing, but we cannot construct a type inference algorithm for Ruby programs. So if we choose subtyping, we cannot infer polymorphic types. If we choose polymorphic type inference, some built-ins cannot be typed. So there is nothing we can do for this currently. So maybe we can wait the advances of type theory. So in the future, some researchers would find a good trade-off. So limiting the subtyping flexibility, but keeping the enough powerful to represent Ruby types, and keeping the polymorphic type inference possible. But we don't want to wait, so we want a type checker within 3 years. So let's double check the problem. When we are talking about the type checking, so we implicitly have 3 requirements about that correctness, static, and no annotations. So usually we want a type checker to be correct. So the correctness of type checker is that if type checker says the program is OK, so then when we are executing the program, no method errors or argument errors will be raised during the execution. The second one is static. So we want to type check the Ruby programs without executing the program. So this means the type checking does not depend on the exact values. So this is a biggest difference from the unit testing. And the third one is that we wanted to type check the existing Ruby programs without adding some annotations or so. So all Ruby programs in the world does not have type annotations now. So we haven't want to write annotations. So, but how about relaxing them? So instead of having correctness, we can have an incorrect type checking. So instead of static type checking, we can try the type checking in runtime. Or instead of inferring all the types, so we can ask programmers to write some annotations. So what can we do if we relax the correctness requirements? So usually the type checker developers want their algorithms to be correct. So, but this doesn't mean the incorrect type checking does not make any sense. So even if their algorithm is somewhat incorrect, but the tools may help the programmers to develop their software. One example is TypeScript. So TypeScript is almost correct, but it has an unsound typing rule. So it has unsound covariant subtyping rules on function parameters. So the type theory says TypeScript is incorrect. But as you know, the typed JavaScript direct is really useful. It improves our productivity. And we can think about another example for like lint tools. So Robocop or Brakeman, I don't know, or other tools. So they are essentially a set of ad hoc bad program patterns. So I cannot think about how they are correct or not, but it is sometimes useful. So we can use the tools and we can find some bugs from your source code. So this is when we stopped keeping the correctness. The next one is what if we relax the static requirements. So there is a paper by the team of Diamondback Ruby. It is just-in-time static type checking for dynamic languages. So it is published for PLDI last year. So it is really good paper. So the algorithm is to type check Ruby programs during execution. So when the program execution reaches at the beginning of a method, it type checks the method body. So this is the example Ruby program defines foo method, and it calls the bar of string. So assume there is no bar method in the string. So the fifth line calls the foo method with a parameter false. So because the x is false in the second line, so it doesn't, the normal Ruby interpreter doesn't try to call the bar method. So if we try to execute using the normal interpreter, it doesn't report the type error. So, however, their type checker tries to type check exhaust, how to say, the both branch of the if. So even if the parameter x is false, it tries to type check the bar method call of string. So it finds out the no method error from that program. So the paper says that just-in-time static type checking is useful because it can find more issues than ordinary dynamic type checking. And it also supports some metaprogrammings. So this is a great benefit of type checking in runtime. So because the type check is done during the execution, so the type checking algorithm don't have to reason about the runtime behavior, but it just checks the types using some introspection APIs. And the third one is to relax the no annotation requirement. And so this is my latest static type checker. So I want to introduce my new type checker, Steep. It is available at my GitHub repository, and you can install with the Ruby gems. So the key ideas of Steeps are, the first, it is gradual typing. So if you type annotations in your program, it type checks. But if you don't write any annotations in some source code, it doesn't check. So if you don't want type checking at all for Ruby's, so in that case, you don't have to write any type annotations. The next one is, it does some local type inference. So programmers annotate their Ruby programs by themselves. And local type inference is provided to minimize the annotation effort. So instead of adding annotations to all local variables, so the Steep infers the types of local variable automatically. And the third one is, it provides another language to define types. So let me show an example. This is a Ruby program with Steep annotations. So the annotations are given as Ruby's comment. This is an annotation to give the type of local variable x. It is an instance of string. The second line is the type of constant, a pathname constant. So the type is pathname.class. So the .class suffix means the type of the class object itself. And local variables types can be inferred from its value. So the last line, it assigns a pathname object to a local variable path. So the type of path is now the instance of pathname. So you may think about why we need annotating that constants. So in Ruby, I don't know, how do you think, but the constants are almost a method. So it is really difficult to identify what is the value of a constant. So we have to consider about the inheritance and module nesting, and the resolution is dynamic. So this is example. So defines a foo class, and in the foo method, it prints the value of the constant foo. So when we first execute that, it prints the foo. It is then it means that the value of foo constant is the class foo. But we can do something like this. Foo : foo equals some string. Then the constant in the foo method is the foo : foo, not the top level foo. So, so because of this, the reasoning the value of constants requires the whole program analysis, and it's impossible to identify the value of constant from one Ruby script. So instead, it is the programmer is responsible for that. So programmer have to tell the type of constant using the annotations. So let me show some type definitions. So types are defined in another language by programmers, and it is not extracted from Ruby programs. This is something like the C headers. So the type definition looks like this. The first one is to define the interface called string convertible. It has a toStr method, and it has to return a string. The second one is to define a string. So it has a split method, and it is overridden. So the first pattern is receives the string convertible instance and an optional integer, and returns an array of string. The vertical bar connects another method type. In this case, it receives a regular expression and optional integer again, and also returns array of string. The optional parameter is prefixed with the question mark. So this is the third class. This is not a built-in of Ruby. So it is the class in your application you define that. So when you are trying to define a class for your application, you have to write its signature. So the method parameter also supports the keyword arguments like this. And this is example of another interfaces. So we can have another interface, and it is each method, and it accepts the block as argument. So we can write a polymorphic method like this. And to use the modules, we can write something like include. It also supports some form of monkey patching. So there is another signature construct called extension. So when you define an extension in signature, it is mixed to existing class. So in this case, the object signature will have a try method. So what is signatures? So in the signature, we define the interface, class, module, and extensions. The interface is the core of the type system, and the class and modules are utility constructs to define the interface. So in the previous example, I showed the person class signature, but it is not directly connected to the type of something like person.new. So there is no relation in Ruby code and signatures in Steve type system. So you always have to specify the type of person constant by annotating that explicitly. So this is to handle some kind of metaprogramming or open classes. So this is the Ruby program. So first, there is an object class defined in the runtime, and assume that we have another object class definition. So maybe active support try or so. Then it means there are at least 2 object class definitions in the Ruby programs. The one is without try method. The another one is with try method. So if the types are directly connected to the Ruby programs, so there will be a confusion that the type object is which one does that point to. So with try method or without try method. So to avoid this confusion, Steve uses another signature language. So this is a summary of Steve. So it has a local type inference and structure subtyping. So this is very similar to TypeScript. Because we declare the method types explicitly, we can have polymorphic types. And we have union types or method overloading. So they are essentially a subtyping. So because we write annotations, we can have subtyping, and we can have union types and method overloading. So another key idea is that the signature and the code are separated, and it also supports some extensions. So maybe this looks very similar to Objective-C. So using the mechanism, Steve does not need to give types for metaprogramming. And it also supports some monkey patching. So I skip about 10 slides. So type inference for Ruby is almost impossible. So and I'm now working for a type checker. It writes the type annotations. And local type inference and structure subtyping works well, I think, currently. And I hope the implementation Steve is a good material to start a discussion about the static type checker for Ruby 3. So thank you.
Do you have any questions?
I have one question. Type signature. Is type signature DSL implemented by Ruby?
The parser is implemented by Ruby, but it doesn't run on the Ruby's context. We implemented a parser using rack, and it parses using the LR algorithm. So maybe it's not a Ruby DSL.
Thank you.
Thank you for your presentation. So maybe we need to write many types with Steve. So how it is difficult, do you think? So I believe Soutaro-san can write every types, but maybe it needs so many time to complete all of methods typing. So maybe we need to write. So so user need to write the Ruby built-in classes and also their own applications types. So what do you think about the difficulty to write such a types?
I think it really depends on how precise we write the types. So for example, we can have the parameter of string, but usually it's something like it returns, it has a toStr method and which returns string. So there are many such the precise true interface and the really rough type name. So if we want the more precise ones, it will be difficult. Is this okay?
Okay, thank you. One more question. Sorry. So sometimes it is difficult and sometimes it's easy. I agree that. So for practical use, so Rails application needs such a type system. So Rails framework, maybe it is maybe Rails framework should provide their own type systems. So but as you know, there are so many source code base of on Rails ecosystem or Rails framework. So is it? Do you think it is feasible? Is it enable to write such a types in the limited time?
In the limited time, I think it's not very easy. So, in my mind, I think it's something like the TypeScript and JavaScript libraries. So there are huge number of JavaScript libraries, but the community, the JavaScript developers around the world write some type definitions for TypeScript. And today we have pretty much number of type definitions for TypeScript. So I want if we can do something like that.
Okay, thank you.
Adding to Sasada-san, I guess it would be beneficial if you have a type annotation which covers all the built-in libraries and at least, for example, active support. And as Sasada-san said, theoretically, it is possible to generate, write down such annotations by community. How can we help you?
How to help me?
How can we help you? How can
Yeah.
the community help you?
So, in fact, we need more and more implementation effort for Steve itself. So, maybe not yet.
Thank you.
Do you have any other questions? It will be the last question for this session.
Okay. Thank you for the great work. I understand Steve is now currently implemented peer review with Rack. Do you want to extend the Ruby core anyway, or do you want to add any feature to aid Steve in Ruby core?
So, having some features in Ruby core.
Yeah.
Yeah, it
Or
may be.
is it enough with pure Ruby?
And maybe it depends on the performance of type checking. It may be an issue. So another one is we want some operators, so dynamic type testing operators. So in Ruby we have is up, but it is to test the inheritance relation. So we want some structural subtyping relation testing operator. So for that, we need the cooperation of Ruby interpreter and the Steve type systems.
Thank you.
I'm so sorry, but you can ask freely after this session. So thank you for Matsumoto-san.